Thank you so much, Raja, and thank you, members of the research team who have joined us this evening. And I see Joel has also now joined. Thank you all so much for being here. We have a captive audience ready for you this evening.
Joel, had Jim come back when you came over? This arena.
Sorry,
Joel,
I had not seen him before I had left.
Okay, I think Arena's in touch with him, so come over. Joel, would be amazing if you could please share your screen for the ASI GUI. That would be great.
Great. Screen sharing is not enabled.
Oh, let me do that. Let me make you co-host. My bad. You should have it now.
Okay.
And I want to explain to the group what's been going on today. It's been an unusual start to the night. And if I get it wrong, please chime in. Even if I do get it, even if I don't get it wrong, please chime in. So we started the, normally we take afternoon calibrations. We take flat field exposures and wavelength calibration exposures, arc lamp exposures. But none of that was possible in the afternoon because there was a power outage that caused the internet on the summit to go down. So we only gained access around 6 o'clock Hawaii time, if I remember correctly. And then, so we had to do our calibration very late. And we decided to do calibrations, the team decided to do calibration because the weather outside was iffy, so we weren't going to be able to open the dome anyway. So there was we were looking at one thing that delayed and another thing that was actually threatening the night. Fortunately, the summit was sitting in a cloud. Fortunately, right around the time it got dark, the clouds sort of receded a little bit. So we're on our first science exposure here, first science target. I think it's the first exposure, right, Joel? It's still on the very first one. Yeah, looks like that. 5 minutes to go.
Correct.
For the first one. And we have on the call today, and as some of you were here yesterday, but we have a bigger group today than we did yesterday, and I would love for the science team just to go around and introduce. So Joel, I'll pick on you first. Actually, Elisa did the introduction yesterday, so starting with you.
Okay. Hi, everyone. My name is Joel Roediger. I am an astronomer working for the National Research Council of Canada. The NRC has a research center for astronomy in Victoria, BC, in Canada. And, we do many activities or endeavors within the, whole enterprise of astronomy at our research center. And so one of them would be doing forefront research in astronomy. So that is what I do in my role there. I'm a research officer with the NRC. I've been with them for the past almost 10 years now. And so, yeah, part of my work focuses on doing research, currently involved in many different types of projects. The one that brings me here tonight is my interest in some of the smaller galaxies that we see in the universe, and trying to understand how the environments in which these smaller galaxies, we call them dwarf galaxies, what kind of impact that has on how they've grown up in the universe. So we're here tonight using the Keck telescope to try and get some insights on that fairly broad question.
Thank you, Joel. That's terrific. Rena, I see you next on my screen, please.
Hi, everybody. I'm Arena, one of the telescope operators here at Keck. So, as I think is true for a lot of telescope operators everywhere, one of my main responsibilities is getting us on target, checking pointing, making sure we get to the correct objects, checking that we're guiding well through the night and that everything stays, all the systems on the telescope are running smoothly. And then my second, although probably more important responsibility is checking, keeping an eye on the weather and making sure that none of the outside environmental conditions get into the dome. So I think Raja mentioned earlier tonight, we had some summit level stuff. So even though it wasn't quite hitting us, kind of waiting to see whether things would envelop us or stay back. And I think that's all I have to say.
How long is this shift of yours? And typically, how long is an OA shift, and how many nights do you get off after that?
We kind of have a schedule. We work 4 nights, and then we have one night before that to acclimate to the summits and the night schedule. So the first night we stay at Halepahaku, which is at around 10,000 feet elevation, and we want to spend the whole night there, and it really helps a lot to get us acclimated to the high altitude. Really helps, for the next night to not get any of the symptoms that can be associated with altitude. And then, we also kind of transition to the night schedule. And then we are actually off for about a week after that, after work shifts, which is great because the first 2 days, you kind of are in a jet lag and you don't really know what's going on. Very zombie feeling, especially that first day getting off the summit. Both because of the altitude, you get like very dehydrated, and then just switching back from night schedule to day schedule, it always takes me a couple of days. So it's really nice to have a few extra days off to do things. Plus, when we're on shift, we're stuck at Halepahaku for the whole time. So it's really nice to be able to go home and see my pets and my happy dog, and get to do a few things on that time off.
So you spend your working hours at the summit and when you're on shift, and the working hours at the summit and the non-working hours at the Halepahaku 9,000-foot level?
Exactly, yeah. In the summertime, that get a little bit of time to we sleep, get a chance to use the gym that we have there. In the wintertime, pretty much just get to sleep for about 6 hours and then get dinner and run up to the summit and do that process for 4 nights, just back and forth.
Yeah,
So it's really nice now we're getting into the, well, maybe astronomers are less happy about the shorter nights, but for our schedule, it's nice to get a little bit of extra sleep.
Oh, that's a good point. Let's see, do we have, Sung-Soon, you haven't introduced yourself, and I don't know if Jim is on. Jim is not on yet. Rena, is Jim going to join? Do you know?
I'll ask him now.
Okay, thank you. Sung-Soon, please go ahead, introduce yourself.
Hi, I'm Sung-Soon Lim. I'm an astronomer working at the Yonsei University in Korea. Yeah, it's a little far from you guys there. Yeah, I'm also working on a lot of astronomy topics, including Dwarf Galaxies. I collaborate with Raja and Joel very long maybe now we are more than 8 years, I think. So I just want to join I'm part of their big collaboration team, so I want to see how it's going on, their observation. So I like this kind of observation. So yeah, Keck is the world's largest telescope, so I love to use Keck. Yeah.
Thanks, Sung-Sung. There's Jim. Jim, we were just going around doing intros. If you want to jump in, that would be great.
Sure. Hi, everybody. My name is Jim Like. I'm a staff astronomer at the Keck Observatory. I support all different types of our observations, including our instrument tonight, ESI. And it's wonderful to be able to join these sessions and meet people around the world who enjoy the science that we do at the Keck Observatory. So glad to have everybody here.
Thanks very much, Jim. I'm trying to remember when ESI was commissioned. Was it 2000 or 1999?
1999. So depending on our audience, there might be some people younger than ESI.
Yes, I think there are. I remember I was 5 years into my faculty position at UCSC, and I was relatively new to spectroscopy. I had done some spectroscopy with telescope in Australia with the autofib instrument on the AAT, the Anglo-Australian telescope, 4-meter telescope. I'd gone out there 2 falls in a row. Really beautiful place, wild kangaroos running around like the deer on the Santa Cruz campus. I was used to seeing deer running around, not used to seeing kangaroos running around. They sort of look like deer, but it looked like deer having bad hair days. That's so I remember going there, and that was my first real exposure to spectroscopy. And I show up in Santa Cruz. A couple of years go by, and the observatory director, Joe Miller, says, "We're going to build a spectrograph. We're going to build a spectrograph, and it's because there's one being built called Demos. We're going to build a spectrograph that's going to be a smaller, cheaper version, but a lot of the software tools we develop for this will help." It'll be like a testing of the Demos thing. So I said, this is great. I know nothing about spectrographs. I've just learned to use them. They said, don't worry, I'll teach you about this. You'll be on the design team. So I learned a huge amount during those years, couple of years, from Joe, who's an expert spectrograph builder. And ESI is not the most simple spectrograph. It's an Echelle with a cross-dispersing prism, I guess. But it has multiple modes. I mean, the IFU mode didn't exist then, but there was a low dispersion multi-object mode that was built in from the start. The IFU came later. Anyway, I was reminiscing about ESI, and I actually started observations with it right away with one of my PhD students, Marla Jiha. She had started her PhD in 1999, the year ESI was commissioned, and she was one of the, she and I were some of the early users of ESI studying dwarf ellipticals. And I was saying yesterday that these things are so darn mysterious that after 20 years of taking spectra and trying various things, observing their globular clusters, observing the main body of the galaxy, we're still struggling to understand DEs as a population of galaxies. Nice mystery. Anyway, Jamika, I haven't asked you to introduce you. Please go ahead if you have a few minutes to introduce yourself.
Thank you, Raja. I'm happy to reintroduce myself to those who joined a little bit later. I'm Jamaica Marshall. I am the coordinator for Shadow the Scientists. You may have seen some emails from me, or if you emailed me, we've had a few conversations. So thank you so much for joining us. And I'm going to stay here for a little bit longer. I'm actually doing some observing myself outside. It's a beautiful evening here in KL. I am maybe 30, 40 miles from the road that goes to Maunakea, Saddle Road. But I am here on the Big Island of Hawaii, and it is beautiful. I have a new set of toys set up outside, some astronomical binoculars. So I'm doing some observing while joining y'all, and it's certainly inspiring to be here with all of you. Thank you.
Thanks, Jamaica. And later tonight, from I guess the STS session later tonight will be from 4 to 5 a.m. Hawaii, right, Jamaica? And then Hero is doing something in the schools from 3 to 4 Hawaii time.
That's right. That's right. But Hero and JP they're going to join that same Zoom link though at 3, because that's what all the teachers have.
Ah, okay. So they join the Zoom link, the Shadow Zoom link.
That's correct.
Okay.
And then they'll just roll into their observing session with the team at 4 a.m. HST.
So from 3 to 4 HST, they won't be on the Shadow link, or will they be?
They'll be on the Shadow link just because that's what they registered with, but the Hero has a presentation similar to what he did before with the students.
Gotcha. Gotcha. Okay.
And I think JP is also going to be helping with that portion.
I think the main thing to make sure is that the science communication that will be happening during that time, he may have to take a couple of breaks when, when need to change targets and things like that.
Oh, yes, yes. He is very flexible, I'm sure. But the 3 to 4 p.m., 3 to 4 a.m. though, he will not be interacting with the team at all. They'll just be using that link for their connecting with the 6 high schools there.
Oh, I see. I see. So he'll be talking to the schools, but we won't be able to hear that, right?
I mean, if you join and you wanted to interact with him, I'm sure that he would absolutely love that. But but for the actual shadow session, that's from 4 a.m. to 5 a.m., just the hour.
Okay, so please send me the link for the 3 to 4 if you get a chance.
Okay, it's just one link from 3 to 5 is how I have it scheduled. It's in the Shadow Zoom account.
Oh, I see what you're saying. So what we can do is the science team will go back to using the Keck link, and but we would ask the science team to join at 4.
Yes.
Perfect. I understand now. Because after this session ends, which will be at 10:30 Hawaii time, 1:30 Pacific, the science team will go back to using the Keck Zoom link. And then if you guys could please come back at 4 a.m. Hawaii, that would be terrific. 3 to 4, we'll use the link, but just to talk directly to the schools without the shadow session on.
Yes, thank you all so much. And I will, you have the login for the Shadow account, for the Zoom account, but I will send you the link.
Thank you, Monica. I have the link. We'll use this link.
Okay.
Is it? Yeah. Wait. Is there a separate Zoom registration for the later one, or is the 4 to 5, or is it this one?
Correct. It is a different link for the RECA session.
Okay. Please send that to me then. So RECA,
okay.
RECA is stands for Red Estudiantes Colombianas Astronomía. So it's a network of Colombian astronomy students. They're going to be connecting from 4 to 5 for a bilingual session. Jeronimo Calderon will be doing the translation from English to Spanish for 6 high schools in Medellin in Colombia. This is the second time they've done this. There is a group of Colombian high schools has joined. I think it's a different set of schools this time than was last time. Last time they did this was in February. I think it was a snowed out night, but they were still, we still had a session, able to look at other images, NGVS images. All right. We have some new people on the call today who weren't here yesterday. Welcome back to those who were here yesterday. Jim, Robert, Rob, I see you. Let's see. I recognize some of the names of the people who weren't here yesterday, but are here today. Ariane, in particular, welcome. And I thank you for completing your application. We're reviewing that. Ariane is a high school student in the Bay Area. So interested in the SIP program that we run, SIP Science Internship Program. This is a good time to, if anyone else wanted to introduce themselves, either by unmuting themselves or typing into the chat, you're welcome to do that. Emily, you're welcome back. I think you're back. You connected from Switzerland then? All right. So what for those of you who've seen this before, I apologize for explaining something you already heard.
Oh, sorry, Raja. I think one of the participants had his hand raised.
Oh, sorry about that. Yeah, why am I not seeing that?
Hi, my name is Kyle Marston. I am very interested in science because my last name has Mars in it. So it's always been a thing for me. I'm happy to join you guys, and I am taking some thorough notes, although I'm not in any way a formally trained scientist.
Thank you, Kyle. Kyle, how did you find out about us?
I found it on Eventbrite.
Oh, wonderful.
Yeah,
wonderful.
I use Eventbrite for a lot of different stuff. Usually I do news kind of things, but sometimes I get to do cool science stuff for my job.
Excellent.
So that's how I found it.
I think Jamaica has started the marketing for STS on a couple of different platforms, and Eventbrite is one of the places. Yeah, that's wonderful. Thank you. Let's see. So I was going to quickly this. I don't know if you probably can't see my cursor, but the main window in this that Joel's sharing, the one that says dashboard 2 KTL, yeah, the one that's highlighted now. You can see Joel's cursor. This is actually a proxy for the spectrograph. It's meant to be a cartoon version of the spectrograph, highly, very abstract representation. But the blue arrow is meant to be light coming in from the telescope. And the different things that the light encounters along its path are shown by these boxes. Some of them are in the light path, some are outside the light path. So one of the first things that it encounters is a hatch. So where the telescope takes parallel light coming from a distant astronomical object, turns that into a convergent beam. That convergent beam comes to a focus at this location that's marked, where it says upper slit, the thing that is the first of the brown boxes that's in the light path. You want the light to come to a focus when it's going through a narrow cut in a piece of metal, a slit in a piece of metal. That metal plate An actual image of that metal plate in real time is what you're seeing in the screen in the upper right. You see the very bright star, but you see a galaxy, and Joel's pointing to the galaxy. Some of its light is going through a cut in a metal plate that's called a slit. It's 3/4 of an arc second wide. It's about 20 arc seconds long, and that light that's going into that metal plate then encounters a Decker. This is the second box from the left. Then it encounters a filter. Right now we're not using a filter, so clear S is where it has what it says. But if you wanted to put in a filter to only admit certain wavelengths of light, that's where it would go. In fact, Joel, if you would click on that brown section of the box, it shows you the options that the filter, I think left clicking on that should, okay, yeah, there we go, sorry. It's a lower button. It shows that you can put different, the I, R, and V filters are like a infrared red, V for visible light, green light filter. And Stockton NB must be Alan Stockton's narrowband filter. And I don't know the difference between, clear I and clear S. Clear filter for spectroscopy, clear filter for imaging is what I'm guessing. I don't know if it's a piece of glass or it's just an opening. Jim is what's the difference between clear?
The clears are openings.
They're just openings of different sizes.
Yeah, so we have to have a there'll be a focus depending on it, because it will be different. A focus will be different without a piece of glass than with a piece of glass in it.
In this case, we're using an Echelle. This is the observing mode box now. And I think if you, Joel, I think you want to select clear S on the, yeah, there we go, okay. And then the Echelle box has multiple options also. Imaging, low resolution spectroscopy, and Echelle. Echelle spectroscopy, which is the highest resolution spectroscopic mode available on ESI, is what we're using. I believe the word Echelle means steps, so it's sort of a diffraction grating that has got notches built into it, like steps. And I think that's what the origin of the word is, if I remember correctly, Echelle. Then you get to control the focus, and finally, disperse light, because it goes, it reflects off the Echelle, goes through a prism. The prism is not shown because it's not something, I think that's part of the whole Echelle package. The Echelle does the splitting of the light into the different wavelengths, but the different orders overlap. And so there's a cross-dispersing prism that separates orders. I think we're using orders 6 through 15 ESI. We'll see that in a different window. Anyway, and then the green box, it's green now because it's collecting photons. It turns different colors depending on what the CCD is doing. It's gray when it's flushing the CCD, it's green when it's collecting photons, and I forget what color it turns when it stops the exposure and starts reading out the detector. But you can see that's 10 minutes to go, 600 seconds is 10 minutes out of 1800 second exposure. So there's one counter counting up. That's the thing that is in the upper right of that larger green box, 12, 11, 12, etc. And there's one counter counting down, which is the thing that says time remaining, which is 500 and something now. And it says 2 exposures in the box to the left of that. That means this is one of 2 exposures remaining. We actually started by requesting 3 exposures and finished the first one. That number automatically counted down from 3 to 2. And when this exposure finishes, which will be another 9 minutes or so, you'll see that the number of exposures will automatically tick down to 1. That will be the last. So we're taking 3 half-hour exposures. So in 1.5 hours, 90 minutes, we get adequate signal to noise for this galaxy. Let's see. Joel, do you have the control one window or anywhere where we can see the spectrum, the first spectrum of this galaxy?
Yes.
This is something we were looking at yesterday. Ah, there we go. Wow, beautiful. You really can see the nucleus of this galaxy. And you could, the galaxies we were looking at yesterday were intercreated.
Yeah.
So you see a very sharp line running sort of more or less vertically, but sort of along these curved tracks. That's the nucleus, the central star cluster, nuclear star cluster of this dwarf elliptical galaxy. You can see it in all the orders. I think it's a little hard to see it in the leftmost order, but I think I can spot it. So that's your orders. Let's see, from the left, it's orders 15, 14, 13, 12, 11, 10, 9, 8, 7, 6. You can see things are petering out in order 6, so reddest wavelengths, because for a variety of reasons, the silicon detector starts to lose its efficiency, sort of approaching the silicon band gap. Many other systems are, that's not the only thing that's causing things to fade off, right? I think there are other things, systems whose efficiencies dropping at these very long wavelengths, the grating efficiency and all that. The reason you don't see much light in the left orders is because we're looking at a fairly old set of stars in this galaxy, and they put out mostly light in the visible and infrared part of the spectrum. They don't put out much in blue and infrared light. And this is a general rule of thumb. When you have old stars, they tend to put out their light at longer wavelengths. Young stars tend to put that light at shorter wavelengths. And these galaxies are composed almost entirely of, well, not almost entirely of old stars. And this is part of the mystery of dwarf ellipticals. They are seen in these cluster environments, high density environments, where they seem to have been cleaned of all the raw material from which new stars can form. And this apparently happened a while back, billions of years ago. So that for the last few billion years, these galaxies have not been forming new stars. You can see that they're sort of aging stellar populations. The stars that we see in them formed a long time ago. And in typical galaxies, there's a range of stellar ages, like Andromeda, Milky Way. They've been forming stars pretty steadily, but maybe at a declining rate. But they're still forming stars. There are galaxies out there like the Large Magellanic Cloud that's forming stars at a pretty steady rate throughout its history. In some episodes where it may have had spikes in star formation, whereas these galaxies formed their stars early and they sort of were quenched. This process of forming stars was quenched. And these are the things we're trying to understand. Why was it quenched? Exactly what led to the removal of the raw material? Probably it's falling into the cluster, falling into the Virgo cluster, where there's a lot of plasma that can run pressure strip material out of the fuel, out of the galaxy. Anyway, I'll stop talking. Sangsoon, Joel, if you want to chime in with any other science points about galaxies, anything at all, really.
Yeah, sure. I'm happy to sort of add on to the explanation of what we've just been looking at. So now what I've switched the display to show what's called a finding chart. This is something that is quite commonly used when people are at the telescope observing astronomical targets. It helps give a sense of what we're looking for when through the instrument, and helping to find it in a view camera, say, and to to align the instrument correctly on the target. So what you're looking at is a finding chart for the galaxy that we're currently pointing the Keck 2 telescope at. So it's a finding chart is a plot of coordinates on the sky. So the what's shown along the x-axis here on the horizontal axis, the acronym RA stands for right ascension. And on the vertical axis, we have Dec representing declination. So these are, the two cardinal axes that astronomers usually speak in when we're, talking about positions on the sky. So right ascension mimics the mimics lines of longitude that you'd look at, say, on an atlas, and declination mimics the coordinates of latitude. So we're looking at a particular patch of sky at a bunch of these dwarf galaxies. All these galaxies inhabit a pretty dense part of the universe. That has a name. It's a very special region of the universe. It's called the Virgo cluster. This is a cluster consisting of thousands of galaxies of all different types of shapes and sizes and masses. Most of the galaxies in this region have stopped forming new stars. Some still are. And what you're looking at here is one particular member of that Virgo cluster. And so this is what's known as a dwarf galaxy. It probably has it's at least 10 times less mass than our own Milky Way, probably more than that, but not more than 100, I would think. And so some of the interesting things, I guess, that you can just kind of extract from looking at this finding chart is maybe one interesting thing is you can look at the scale down here, this scale bar, 1 kpc. So that refers to a length on this image, known as a kiloparsec. This is a very common unit that extragalactic astronomers speak in. So 1 parsec is roughly equivalent to about 3 light years. So now we're talking about 1,000 times, so about like 3,000 light years. And so why I point this out is you can immediately you can kind of look at that scale bar and then compare it to what you see in the image here, and it sort of gives you an idea of what are the sizes of dwarf galaxies. So in this particular case, it probably, like, the center of the galaxy would be about here where my cursor is pointing. So this would from one end or from the very center out to the edge of this galaxy, if I'm eyeballing it, maybe that you could sort of see the galaxy extending over, say, 5 kiloparsecs, maybe, give or take.
Joel?
Yes.
Sorry. One of the ACS actuators is kind of starting to step out of line. Here, we might be able to roll through a 30-minute exposure, but I'm wondering if there's an easy way that we can interrupt the sequence and maybe try troubleshooting it and then coming back to this.
Jim?
Yeah, we can just it's reading out right now. The second of the 3, right? So we can pause. Pause the sequence, and then we can work on the. Work on the mirror. So when the readout is done.
CCD readout complete.
So it's going to go right into the new image. So maybe right after the erase, you could click on the stop exposure button and just hit the pause.
Okay.
And that should pause it. Or yeah, hit the
Should we,
pause button.
should we stop it and abort the exposure and just start and do another one afterwards? What's
Yeah, we can do that. We can do that. We can just stop it.
yeah, that way it
So-
won't collect cosmic rays.
Okay, I'll stop it now then.
And I'll go ahead and troubleshoot this to see if I can get it back into stack.
Okay,
I'm gonna read it out.
sure.
Exposure complete.
I didn't completely understand what the glitch was.
Go for it, Arena.
Okay.
So it's one of the actuators for the primary mirror
Oh, okay.
is causing some issues.
This is the ACS system, the active control system.
Mhm. Yeah.
Got it.
So it's not too far out of stack, but you know, if it starts stepping out farther, it pull one of the segments out. And then we could lose that light.
Readout complete.
All right, stand by. I'll let you know how things go on my end.
So folks,
Okay.
what you're experiencing is something that is as much a part of doing science as, you know, when things were sailing smoothly and we were collecting photons from the distant, you know, from a galaxy 50 million light years away. What is happening right now is the control system that keeps the 36 segments of the Keck telescope in alignment is, use a technical term, acting up. And so Arena's going to troubleshoot that. And as soon as that's done, we will take the third of the 3 half-hour exposures. We finished 2. It was sort of convenient that it happened right at the end of the second exposure. We didn't have to split up the second exposure into multiple parts. So, but these are very complex instruments, of course, multi-component instruments, the telescope and spectrograph. So complex bits of software as well that control these components. So so this is sort of something you learn to live with and work around and problem solve around.
So while Arena is working on that, I'll just try and finish up on this finder chart. Sort of what are the most salient aspects, I guess, from that. So I mentioned that you know, we can sort of glean a little bit of information just by looking at this image about the size of this galaxy. One of the interesting things, and I think this was this really showed up very clearly in the ESI exposure that we showed you before. So if I zoom in on this finder chart, what you're looking at here, this red rectangle represents the slit of the spectrograph. And so we've aligned it with what's called what's called the major axis of this galaxy. So if you were to run the or galaxies, when we see them on the sky, they tend to have these elliptical shapes, and so ellipses are defined as a shape. They have this major axis, and so we've aligned the slit for our observations with this major axis, so that way we can collect as many photons as possible from this galaxy. But what I want to point out to you here is this this compact bright object right in the center of that galaxy. So that is a nuclear star cluster that's found right at the central regions of the galaxy. So these are star clusters. They, I guess, in many ways, you might think of them as being similar in some respects to globular star clusters that we see around our own Milky Way galaxy. But they they tend to be much more massive than a single globular cluster, and so they're still kind of the enigmatic objects. We don't really have a full understanding of how these star clusters at the centers of galaxies are built up. But you can see with the way we've set up the spectrograph is that we sort of intersect not only the stars in the main body of the galaxy, but we also are collecting photons from this nuclear star cluster. And that was that really bright line that was running up and down through all those orders of the spectrograph that you saw there. I thought one other thing I would point out to you based on this image is, so I was talking earlier about this scale bar representing like a typical distance that we astronomers care about. So for kind of contextual purposes, we know that the sun that we orbit on the Earth, the sun sits about 8 kiloparsecs away from the center of our own galaxy. And so when I mentioned earlier, the scale of this dwarf galaxy, by eye, you might say it's like it's sort of peters out after about 5 kiloparsecs. The stars really disappear at that point. So 5 kiloparsecs compared to the sun's position, which is 8 kiloparsecs in our galaxy, sort of gives you an idea of how much smaller these dwarf galaxies are than our own Milky Way galaxy. And I think maybe just the last thing to sort of point out, you see some of these really brighter objects in that overall field of view. So these would be stars within our own galaxies. So, when we look out with the telescope, we're seeing everything that's along the line of sight. So if there's stars in our own galaxy that just happen to be along that path, then when we take images, we're going to see them too. And so in these particular images, they were quite bright for the length of exposure that was chosen. So you get these really striking bleeds, trails coming off the star. And then additionally, you can see all around surrounding this galaxy are many other galaxies that are again along the line of sight, at much greater distances than this galaxy that we're talking about here. And it's kind of interesting, I guess, maybe just to browse, around this image and look at all of these other galaxies, and you sort of makes me think anyways of this special time that we're living in right now, where the James Webb Telescope is
okay. Sorry, Joel. I think we're back.
okay.
It doesn't seem to be acting up now. We'll have to wait, but why don't we go ahead and start this next exposure, and then I'll let you know if anything else happens to
Terrific.
it.
Okay, thanks, Arena. Yeah, starting now. Okay. Yeah, so when I look at this and I see all these, hundreds or thousands of galaxies that show up just in this one image of the galaxy that we're presently interested in, makes you think makes me think of anyways James Webb, and it's looking at all of these really distant points of light in the sky, and one of its main science goals is trying to find really distant galaxies, right? And find out in that process, trying to understand, how early in the history of the universe did galaxies form, and really like, very dramatic examples, extreme examples of galaxy formation, galaxies that are forming just hundreds of millions of years after the Big Bang. So maybe makes you wonder if some of these really, compact, very red things, maybe they're some of these really earliest galaxies in the universe. It takes a lot of telescope time and a lot of effort to really just try and figure out, where these galaxies actually sit in the history, in the timeline of the universe. We have to choose our targets pretty carefully, shrewdly. Sung-soon, did you want to say anything maybe about this image? One of the things I was thinking of that maybe you could speak to about this is, I didn't say anything about globular clusters, but of course we know that other galaxies have their own collections of star clusters that orbit them, and you certainly care quite a bit about that. Was there anything you want to say at this point?
Yeah, actually, I should leave in a few minutes, but yeah, I can chime in for a little bit about the globular clusters. Maybe some of you know Galaxies has globular clusters, including our own Milky Way. So maybe you can see some of a little bright, not very bright object in these images. Maybe they should be globular cluster candidate included in this galaxy. Especially the numbers of globular clusters in each galaxy is usually correlate with the mass of the galaxy. So we can expect that we can find some or a little number of a few globular clusters in these less massive galaxies. So when we observe like this kind of spectroscopy keep doing, we usually also observe globular clusters because they are a little brighter than other light from the individual stars. And so that give us some information to study this kind of galaxies. So, but sometimes globular cluster even it's also fainter to observe. So we cannot observe that kind of globular clusters, but yeah, maybe Raja have some spectrum of globular clusters with his collaborator, maybe, or not. So so for the dwarf galaxy, interesting thing is we can find a little more globular clusters than expect its luminosity, based on this luminosity. So sometimes we think about that globular cluster number represents it has more mass than our expectation, but still it's a little, how can I say, it's a little tricky. So, but especially for this kind of dwarf galaxy in the galaxy clusters, usually have more dark matter, which we cannot see in this visual light. So we can find more globular clusters easily in these dwarf galaxies. Yeah, there are many interesting questions about the globular cluster properties, this kind of galaxies, but it's still, how can I say, we cannot understand clearly about that same as the origin of dwarf galaxies or evolution of dwarf galaxies. Yeah, so because I'm very concerned about my time, so sorry for the very quick explain about that kind of things. Okay, so brother also, yeah.
Thank you for joining. I appreciate it.
So yeah, thanks, Sung-Soon. That was great. So I as soon as Sung-Soon started talking, I noticed that there was a couple of messages posted in the chat. So Tim Clark was asking, is there any indication that there is a black hole in the galactic center? So yes, there is. Primary evidence of this is that by studying the movements of stars in the galactic center that's the strongest piece of evidence that we have for the existence of a black hole in that location, and not just any kind of black hole, but a supermassive one, which means that it has on the order of 1 million times the mass of our sun within it. And so actually this was the existence of the supermassive black hole in the galactic center was work that was established based on observations that were done with the Keck telescope itself. So one of the most recent recipients of the Nobel Prize, Andrea Ghez, was one of the leaders of this kind of effort to reveal the existence of this supermassive black hole, and through the use of adaptive optics and coupled with imaging at near infrared wavelengths, and studying pointing the telescope at the galactic center, over many years, because although things happen, things move quite quickly, on astrophysical scales, the distances typically are really great, so are really large, so you still have to look over long timelines, long baselines of time to actually see motions of things on the sky. But yeah, that's so based on how things are orbiting, how stars in the galactic center are orbiting, was how we've uncovered the existence of a black hole in the center of the galaxy.
Quick question, actually. Sorry to interrupt. Is the third exposure started, or are we waiting for Arena?
No, we started the third exposure.
Oh, started the third one. Okay,
Yeah.
sorry, I couldn't see it because
actually, I can switch the share back so we can sort of.
No, this is fine because some of the questions are about this. So I thought you.
So I think we're not. Raj's internet there is a little unstable. Maybe while we wait for him to reestablish connection. So Jim Rea, I'm not sure which way if I'm pronouncing that correctly, but Jim was asking Ray. Sorry, thank you, Jim. Was asking what instrument was used to create this finding chart. So very happy that you asked this question, Jim, because it's the answer is it was a part of an imaging survey of this Virgo cluster that I mentioned earlier. It was part of an imaging survey conducted with the Canada, France, Hawai'i telescope and its MegaCam imager. So the CFH telescope is a neighbor of the Keck telescopes on the top of Maunakea. It's a 3.6 meter telescope, so it's got a lot smaller of a primary mirror than Keck. It was built back in the 1970s. Was when it first started observing, and is still around to this day, still doing forefront astronomical research. So a team of astronomers used this CFH telescope to image the entirety of the Virgo cluster, over 100 square degrees of area on the sky. And they did this in several optical filters. And so that gave us all of the images that we used to create this finder chart that you see here. So this is a 3-color image where I took cutouts of this galaxy in these different filters. I think what I used for this was the filters U, G, and I. So U would be the bluest filter that we observed this cluster in. G is the next reddest filter, and I is the reddest. So using an RGB scheme to combine the images through those 3 channels to make this the image that you see before you. So it was a concerted, so with this imaging survey, which we called the Next Generation Virgo Cluster Survey, the principal goal was to remap this Virgo cluster at optical wavelengths, going down to very sensitive depths, or very, very to very faint surface brightnesses, so that we could see, not just this dwarf galaxy, but we could see many, many new galaxies in this cluster. So if I were to say, so let's say that this galaxy that you're looking at here has a mass of about, say, 100 million stars, then with this survey that my collaborators and I have conducted with the CFH, we've found new galaxies in Virgo that are as faint or as small as say like 1 million solar masses. So 100 times smaller than this, and there's thousands of these things in this cluster. It's sort of been a bit of a rewrite of our knowledge of what exists in this, very, it's quite a landmark environment, to be sure. I don't think we've gotten Raja back. I think he dropped off on the call, but if anyone else has other
No, I'm
questions.
back.
Oh, you're back,
I'm back.
Raja. Okay,
Sorry about
great,
that.
great.
I temporarily lost my internet connection, so I'm back.
Great.
But I cut out at a critical time. Was Tim's question about the black hole at the center of this galaxy or the center of our own galaxy?
Ah, well, that's a good an interesting distinction. So I'm not quite sure. I took it to be big G galactic.
As in our galactic center.
Yeah, but yeah, that's another sort of question entirely. If there's a black hole in the center of this galaxy that we're showing.
So this is in fact what Marla and I had set out to do as part of her PhD thesis back in the late 1990s and early 2000s, and we found that there are these nuclear star clusters. Is that caused by a black hole? That was a question. Intermediate mass black hole. If they are, you expect the velocity dispersion to rise at the center of the nuclear. I mean, we were trying to understand the nature of these nuclei in dwarf ellipticals. Are they caused by black holes? Are they just normal star clusters without massive black holes? And we found in the galaxies we studied, only one of them had a spike in the velocity dispersion of the center. The others, it actually got dynamically cooler in the center. So there was a dip in the velocity dispersion at the center, which would be arguing against the presence of black holes. So it's not an easy measurement. It's not an easy determination to make whether these things have black holes at their centers.
Does anyone else have a question they would like to ask, either through chat or through Mike? While we wait for people to think about that. So I could also point out that we have the telescope for the full night tonight. So might be on this for another, say, 8 hours or so. That would take us all the way, past sunrise or to morning, twilight, and dawn. There's always a bunch of things you could do at the end of the night, but so we are, I mentioned, observing galaxies in this Virgo cluster. So at this time of year, we can observe Virgo for like about 7 hours or so. But the full night, we have darkness for, say, close to 10 hours. So that leaves us with a bit of extra time to use up. And so one of the other things that we're going to be observing later in the night, after Virgo has set on the sky, will be stars in our own galaxy. We're going to be looking at least two of these are known as two stars in the halo of our own galaxy. These are variable stars known as RR Lyrae, and this is the observations that we're going to be taking for that as part of a project that Raja and a PhD student of his at Santa Cruz are leading up to collect information on the motions of these stars in the outskirts of our own galaxy. So I don't know, Raja, if you wanted to say a word or two about that.
Yeah, I'm happy to say just a couple of quick things about that. So I'm putting the student's name, Yuting Feng. This is his PhD thesis at UCSC. Is on RLR. In fact, he has discovered some of the most distant stars known in our Milky Way galaxy, RLR, that he's found. We are just getting ready to submit a paper on that. We had a press release about this at the AAS at the American Astronomical Society meeting in January. But in the spectra that we'll take after Virgo has set of 2 RLR, they are located about 90 kiloparsecs from us, so roughly 90 kiloparsecs from the galactic center, because we're only 8 kiloparsecs away from the galactic center. And this is sort of looking in a perpendicular direction from the line joining us to the center of our galaxy. So, so the spectra we'll be taking are of stars that are about 90 kiloparsecs away, and Yuting has found stars that are up to 300 and a little more than 300 kiloparsecs away. So these are the most robustly detected and of these very distant stars to date. So, and RLR are strange stars because they pulse. It's not easy to measure their velocity, because when the thing is expanding, you get a false velocity. When it's contracting, you get a false velocity. You don't get its center of mass, you get its surface, which is moving towards you or away from you, depending on whether the star is expanding or contracting, relative to the star's center of mass. So this is one of the tricky things about measuring their velocities. I'm putting Yuting's name in the chat.
Sorry to interrupt everybody, but I'm going to sign off for the evening. So
Okay.
good luck.
All right.
Jim.
Give
Thanks,
a call
Jim.
if you need.
Okay, will do. So yeah, so tonight's kind of schedule for us, it's pretty action-packed. I'm hoping that we'll be able to observe maybe 4, more likely 3 galaxies in the Virgo cluster. The reason we can only observe that many is really just dictated by, you know, our estimations of how much time that we need to expose the instrument on each individual galaxy in order to hit a certain quality of data, or what we call signal to noise. So the first galaxy that we have been observing tonight, I'm going to switch back to this window. So we've dedicated about 1.5 hours of just open shutter time. You know, there's other sort of costs, as it were, right? When you move the telescope and that sort of thing, that takes up a certain amount of time. But so we're observing this first galaxy for about 1.5 hours, and then subsequent galaxies will be pointing to, will actually be even exposing longer, up to 2 hours. So it the reason I guess that I would say that that we you know, spend so long on these galaxies is you know, they're pretty faint. Most of a good fraction of the galaxy sits below the you know, background brightness of the sky. So you know, we need to try and collect many photons, lots of photons from these galaxies in order to be able to do the science that we want to do. So you can see here on our on the dashboard here, we are just under 400 seconds left on this galaxy. I can actually show you how I interact with our telescope operator, Arena, to decide, okay, where are we going to go to next? So I've already, for the plan for tonight, have decided, okay, we're going to start with this one galaxy that we call VCC 786. And within this magic GUI, I can highlight our next target. And so then I can say, then when we're finished exposing on this one galaxy, we're going to be ready to move to the next one. And so I then will ask Arena to move the telescope to that one. And so then she will point the telescope to that, you know, to these particular coordinates. So you can see the coordinates of the galaxy right here, the right ascension and declination. And then we will set up the instrument on it. More or less, so what that involves is positioning the slit to be over top of the center of the galaxy. And then we want to make sure that we just have the right orientation of the slit to maximize the amount of photons that we get from the galaxy. So I see we have something in the chat. Okay, so we have a question from Jason Keys asking, is this a single exposure or stacked multiple exposures? I'm not quite sure, Jason. I think you might be, I think you submitted your question when I was still showing the Finder chart. So I'm going to assume that that's what you're referring to. So that's what you saw there. Yeah, that was multiple exposures. And so often when we are imaging galaxies or any astronomical object, we will execute what's known as a dither pattern. So we don't just expose one particular you know, pointing of the telescope, but we'll actually do several different exposures, have many different with small offsets between them. And often or one of the main reasons that we do that is because when we have these large format CCD mosaics. There's these little gaps between individual CCD chips in the mosaic, and we want to, depending on what the goal for the imaging is, you might want to fill in some of those gaps, and so using a dither pattern is a way to achieve that. So this would have represented multiple exposures taken in multiple filters. And then there's another question here from Kyle. So are there examples of standard candles in the Virgo cluster that we can detect? Is that how we've determined how distant they are relative to us? And then bonus question, can we talk about using gravitational lensing observation and what possibilities that can have in seeing deeper back in time and space? Good questions. So for standard candles, yes. So that's one of the, or that's basically how we establish the extragalactic distance scale. So standard candles would be things like type 1a supernovae, Cepheid variable stars, the brightest red giant branch stars in galaxies. There's also a technique known as surface brightness fluctuations. So we indeed have established distances to individual galaxies in Virgo using some of these techniques. One of the ones that I'm most familiar with would be surface brightness fluctuations. And just sort of roughly what that means is that when you look at a galaxy and you look at the brightness within individual pixels in your image, what you'll notice is that there is a variation from a smooth fit to the galaxy light distribution. There are small variations in the around that smooth profile, and we can use that through calibrations to establish the distance to a galaxy. And how that works is basically that the brightest, it's a variation, that the variation about the smooth fit essentially represents the variation in the number of very bright stars. So like your red giant branch stars, your asymptotic giant branch stars. And that the size of that variation is going to correlate with distance to the galaxy. Very roughly speaking. I'm not an expert in that distance determination, but
I can go a little bit deeper into this.
Great,
so
thanks.
What happens is there's a beautiful cancellation that happens in astronomy. The thing that Joel mentioned, the brightness within a pixel. If you take a galaxy and you move it 10 times further away, the brightness within a pixel doesn't change because each star within that pixel gets 100 times fainter when you move it 10 times further away. But there are
sorry, Raja, I just need to interrupt you for a second to
sorry,
speak to Arena. Arena.
Yes.
Our next target will be number 1, please.
Okay.
Great.
And so you think we should go ahead and validate it by 90 again?
Yeah, I haven't had a chance to upload the revised star list yet, so please do execute that for us.
Okay.
CCD readout complete.
So here in the magic viewer, you can see how we're moving the telescope. Things are whipping by on this guider view. And I think that's our galaxy that in this upper part right here. So contrary to the previous one, this one looks like it's quite a bit rounder.
Yeah, I don't know. Can you tell if that looks like the correct orientation. A little hard to tell.
Yeah,
Maybe
in this
that looks a
case,
little.
yeah. So when we have rounder galaxies, the orientation of the slit doesn't matter as much.
Okay.
But still, yeah, we'll put in the 90-degree change, please.
Okay. Yep.
Yeah, the semi-major to semi-minor axis ratio for this galaxy is about 0.93. So yeah, it's pretty round galaxy. So you can see, yeah, Arena's now moved the telescope to align the galaxy on the slit. You can see all this.
We
Go
are
ahead.
good to go.
Okay, great. So you can see here, this is our slit that we're observing with the 0.7 arc second. Now it's we have the galaxy sitting in the middle of that slit. So we're going to continue with exposures of half an hour, and in this case, we're going to do a set of 4 exposures. Oh, and I just need to update the label of the object here. And we're ready to go. Okay. Sorry, Raja, I was
No problem at all.
like
No,
the interruption there.
Well, this is time critical
It's
interruption.
yeah.
Of course.
Like target of opportunity type of interruption.
Waste telescope. No. This, you can't waste telescope time at all. So no, this is, I'm really glad you interrupted. What I was so this thing that's the brightness per pixel is something called surface brightness per unit area, or surface brightness. Now, it turns out that if you take a particular galaxy, any galaxy, and you move it further and further and further away, or closer and closer and closer, the brightness per pixel, let's say you're in a part of the galaxy that is where the brightness isn't changing with radius, so it's a flat part of the galaxy, right? If you look at that, the brightness per pixel doesn't change as you move it further and further away. And that may be counterintuitive, because as you move a galaxy further away, each star with it gets fainter, looks fainter to us, but there's a beautiful compensation that goes on. If a pixel is a particular patch of the sky, a particular area of the sky. So if you take a galaxy and you move it, say 10 times further away, each star within that, within the galaxy gets 100 times fainter, but that patch corresponding to a pixel becomes 100, it corresponds to 100 times bigger area, physical area, as you move the galaxy 10 times further away. So there are 100 times as many stars. Each star is 100 times fainter. Those two factors cancel exactly, and the surface brightness remains the same. Now, that's all good. So surface brightness is a distance-independent quantity. However, the thing that does change is when a galaxy is further away, there are a lot of stars contributing per pixel. When a galaxy is close, there are very few stars contributing per pixel. And when you have very few stars contributing per pixel, you see greater variation from pixel to pixel, because you see, this is just what's called Poisson statistics. If there's let's say 25 stars per pixel, you expect the variation in that to be plus minus 5. That should be the square root of 25 is 5. Whereas if you have 1 million stars in a pixel, you expect the variation of that to be plus minus 1,000. Plus minus 1,000 out of 1 million is a tiny fractional variation, whereas plus minus 5 out of 25 is a huge, is a 20% variation. A couple of scientists years ago, they were both postdocs at the Institute for Advanced Study in Princeton, Don Schneider and John Tonry. They developed this technique. They said, we can actually figure out the distances to galaxies by measuring how much fluctuation there is in surface brightness from pixel to pixel within a galaxy. And as Joel said, you have to calibrate this. You have to take galaxies of known distance so that you can calibrate this properly. And so Tonry and Schneider, John Tonry, Don Schneider, ended up developing this technique. It's called SBF, surface brightness fluctuation. And I have a couple of personal connections to this, which is Elisa Toloba, some of you met yesterday. She and I use surface brightness fluctuations to measure spectra of distant galaxies, but that are too distant to see individual stars. And the other connection I have is Don Schneider and I wrote many papers together at the Institute for Advanced Study in the sort of early 90s. So I've known John Tonry for a while also, but Don and I became really close collaborators. We wrote a bunch of papers together. And I'm sorry if that went by too quickly, but SBF, you can read up on SBF, surface brightness fluctuation. Sort of coupled to three things. Poisson statistics primarily, the notion that stars get fainter as they get further away, inverse square law, and third parameter you have to consider is a pixel is a fixed area on the sky, but corresponds to larger and larger physical areas as you get further and further away. So those three concepts sort of tie in together to produce to make SBF a distance indicator.
And then, Tim, you had a question saying it looks like you arranged the galaxies in order of RA. Is that to reduce the time needed to slew the scope? That was so when we prepare for observing on the telescope with Keck, we submit what's referred to as a star list, and so that contains the essential information that's needed to decide where do we have to point the telescope, how do we want to orient the slit of the spectrograph. So in this case, the order of the targets, we're not actually going sequentially downward on that list. The targets that we're all looking at, they're in a pretty small patch of sky, relatively speaking. There's over 30,000 degrees of sky around us, and the scale of the Virgo cluster is 100 square degrees, so it's pretty quick to move actually between targets and in this one environment. So the way we're actually working our way through this list of targets is we started with our brightest ones in terms of their central surface brightness, and then we're going down to progressively fainter objects. You're welcome, Tim.
Joel, it's 41,000 square degrees, 41,250.
Yes, thank you.
The way you do that is, I just did that by taking 4 pi, which is the number of steradians in the sky, and multiplying that by the degree to steradian converter, so 180 over pi. Square of that, 180 over. Because steradian is like a radian squared.
So Tim It's asking, are there different types of dwarf galaxies? Yes, absolutely. I guess it kind of depends on what you mean by type, but sort of the canonical, I guess, sort of axes or categories that we tend to think about galaxies, or the fundamental kind of parameters that we think about them, would be things like, first and foremost, are they star forming, or are they quiescent? So quiescent means that they're not forming new stars. So we find dwarf galaxies in both kind of categories, or at various levels of present day star formation. We can also think in terms of their the motions of the stars within them, and Raja would is the expert on that for us. But I would say, yes, we do see, we see variations of that. They tend to be, my answer would be that there's not as much ordered motion in dwarf galaxies as, say, like something like the Milky Way. But, actually, so Elisa, she's done a lot of work with Raja in the Virgo cluster, looking at the dwarf galaxies there, and measuring the internal motions of stars in them. So yeah, so actually I should just hand that part over to Raja. But I guess short answer, Tim, is yes, we do see many different types. But Raja, if you want to expand on any of that.
I think they're primarily, as you said, Joel, there's star-forming galaxies and the galaxies that are not forming stars. And there seems to be an interesting dichotomy. That is, the galaxies that are dwarf galaxies that are forming stars tend to live far away from other galaxies. They tend to be in low-density environments. They tend to live far away from large galaxies. This is an empirical finding. We don't understand there are theories for why, and then. By contrast, galaxies that have stopped forming stars, dwarf galaxies that have stopped forming stars, tend to be in high density environments where there's lots of other galaxies. So no surprise that we are studying these quenched dwarf galaxies that have stopped forming stars. Where are we studying them? We're studying them in the Virgo cluster, where it's got a high density of galaxies there. And again, Marla, one of my former PhD students, has done some recent work on this, where she used the Sloan survey to really look beyond the Virgo cluster, look with many galaxies over a large volume of the universe. And she sees this trend that below a certain mass, so below a certain galactic mass, there seems to be an almost complete lack of star-forming galaxies close to big galaxies. So close to big galaxies, the only kind of galaxies you see at low mass are quenched, star-forming stars. Now, in our own galaxy, the large and small Magellanic Clouds are exceptions to that rule. There are two dwarf galaxies that are forming stars, and they're quite close to our galaxy. But if you look around Andromeda, for example, all the dwarf galaxies around have stopped forming stars that are close to Andromeda. Most of the small galaxies near the Milky Way have stopped forming stars. Like I say, those two galaxies, LMC and SMC, large and small Magellanic Clouds, are exceptions to this rule. And people think they're falling in. We've caught them in their first infall. They're falling in for the first time. So there hasn't been enough time for the quenching to have happened yet. So that's a good question. Different types. How much Gatorade do these galaxies need to restart star formation? No, it's good you're talking about quenching of thirst. The quenching term that's used is sort of referring to, if you think of star formation as something being on fire, quenching is like putting out that fire, sort of by removing fuel. But quenching is indeed used for thirst as well, not just for quenching fires. We've had a really vibrant set of questions today.
Yeah, it's been fun.
Yeah. So this particular galaxy that's on the slit right now doesn't seem to be particularly, it seems to be quite round. Its isophotes are. I didn't see an obvious major minor axis. Unlike the previous one, it was quite elliptical. Also, this one doesn't.
Yeah, so here's the finding chart for this galaxy that we're on now. So yeah, you can see it. Its shape is quite round. Yeah.
And is that red rectangle the size of the ESI slit?
Yes, it should be. Although the width is most certainly been expanded just to probably be able to see the confirm that I placed the slit on the nucleus, I think.
Right, and I see that the length of that red rectangle is about 1/3 of a y-axis tick mark. A y-axis tick mark is 1 arc minute, and so a third of that would be 20 arc seconds.
Mm-hmm.
What is the other star that's circled? Is that like an offset guide?
Yeah, that was when I at one point was thinking that we might have issues centering on our targets, or just as a hedge. Anyways, it was.
Well, that's a good move.
Yeah. So I mentioned earlier that these images come from this survey that Raja and myself, this collaboration that we're a part of, that is generated. And so one of the nice, what we call data products from this has been this catalogs of all these objects that we found in this imaging. And so I was able to use these catalogs to go and look for what are called offset stars. So anytime you are wanting to set the instrument up on something where, maybe it's quite faint, you would have a hard time finding it in a guider camera. You can use, if you know the coordinate differences between where you want to point and some brighter object like a star, then you can set up the instrument on the star and then basically just do this a shift of coordinates to put the instrument onto the object that you're actually interested in. So this was an exercise that I went through in the lead up to these nights with the telescope, was to go and so thanks to this NGVS survey, we have all these things right at our fingertips. We don't have to look too long and hard to find them.
Good point. Yeah. So I'd like to, while you have this image up, I'd like to come back to something that you talked about earlier about RA and Deck being like a latitude and longitude. Sorry, RA and Deck being like a longitude and latitude respectively. It's very interesting if you think about how, why do we connect them to longitude and latitude? It's because, we are measuring these coordinates from our perspective here on Earth. And, if the Earth was static, if it weren't spinning, and if it weren't going around the sun, just completely static, or if you, another way of thinking, if you just take a snapshot in time to freeze the motion of the Earth. And what you can do is you can put people all over the Earth and ask each one to report their latitude and longitude. And if they did that, the star that would be directly overhead to each person, you could ascribe it celestial coordinates that are equal to the latitude and longitude of that person. If the Earth were completely static and not moving, and that would be our celestial coordinate system. But of course, the Earth is rotating. It's not, so you can't quite do that. So a person who's standing on the equator, as the Earth rotates, they sweep, their overhead sweeps through different stars in the sky. We know this from experience that in the course of the night, the sky appears to rotate. The rate of a full circle every 24 hours. And so the RA axis is actually measured in time units. You'll see that 12 hours, 24 minutes, 4 seconds. And so, and it's exactly because of this, that it is, if you have a person standing at a declination of, at a latitude of 12 degrees latitude, plus 12 degrees in the Northern Hemisphere, and let's say 53 arc minutes, actually would be 1253. The latitude was 1253, and they were standing at that latitude. What would happen is every second, the RA that is directly overhead would be changing by 1 second of RA. An hour later, it would be 1 hour of RA would be, the star that's overhead would have advanced by 1 hour in RA. That's why the RA axis is measured in time. It's a practical consideration for having to do with how we observe the heavens from a rotating platform. I'll give you one other tidbit about this that I find absolutely intriguing. We measure time using units of hours, minutes, and seconds, and we measure angles using units of degrees, arc minutes, and arc seconds. A degree is 1/90th of a right angle, and an arc minute is 1/60th of a degree, and an arc second is 1/60th of an arc minute. But and it had never struck me when I first came across these terms that I could see there were these parallels, but I didn't know why. And one of my colleagues pointed out that the reason we call a minute, the reason we call that unit of time a minute, is because it's a minute part of the main unit. The word minute means small part. And so the word minute actually just means it's a division, small unit, small division of the hour. And the reason it's called a second, it's the second time you divide the unit. And apparently in Newton's Principia, it refers to the first minute term, the second minute term, and the third minute term. And the third minute term would be what we would call 1/60th of a second. And so when you do this for angles, you still use minutes. So degree, minute part of a degree is an arc minute, a minute part of an arc minute is an arc second. It's the second time you do the division. A little bit of astro trivia, time trivia, unit trivia. Thanks, Kyle. Thank you.
Have a great night.
You too. Take care. Please
care.
be back. We have a full session. We have a full schedule of these through the year. There'll be 2 more coming up this week, actually. 2 more STS sessions coming up on Tuesday and Wednesday nights, and then we have sessions in May, July. Nothing scheduled in June yet, but things may come up. So, but thanks for joining. So I know Jim has called it a night, but Joel and Arena, we'll end this shadow session in a few minutes, and technically this runs until 10:30 Hawaii time, 1:30 Pacific. We'll end it then. Please feel free to go back to the Keck Zoom link, but please come back to I'll send you a link. Please come back to it at 4 a.m. Hawaii time. That'll be for the group in Colombia. I'll send that link out to the 2 of you by email. It'll be a different link from this one.
Okay.
The same way, I'll register you both. You'll get 2 links for that session.
Sounds good.
Thanks. Well, considering everything, the mirror glitch and the power outage and the cloud, touch wood, we're not doing badly here. Going through galaxies one at a time.
Yeah, and I think the seeing's been on our side at least.
Is it
No
remain
issues
0.8?
there. On the guider, yeah, it's looking quite nice.
Okay.
Yeah.
I think I'm going to sign off also, but thank you to all of you guys.
Thanks, Jay.
You're welcome, Jim. Thanks for coming out.
It's always fascinating. And I'm sitting here Googling away in addition. It always most interesting Google searches come out of the discussions here. All right, talk to you later.
Take care. Take care.
Okay. Bye-bye.
Raja, I have one last question for you. Your earlier comments about how these dwarf galaxies appear in clusters or by themselves, kind of correlating with their star forming and their quenched states. Also makes me think about how we're told that the universe is arranged in like fabrics of threads and knots and voids. Do you see that same kind of similarity, or do you care to comment on any relationship theory that you might have that correlates those?
You know, there is some well-developed theory of how galaxies form. People do these very detailed calculations, and these, as you said, there are these sort of knots and filaments, and these filaments often contain ionized gas. These filaments and knots contain ionized gas, and the voids contain, you know, either little or none of this ionized gas. And this ionized gas, it has friction associated with it. If you're trying to move another gas cloud through this ionized gas, it'll, you know, exert some drag. And we think that you know, that's the essence of ram pressure. We were talking about ram pressure stripping yesterday, but that could well be why galaxies that are, these filaments and knots also correspond to a high density of galaxies compared to the centers of the bubbles, the voids. So it's not the galaxies themselves, but the ionized gas that is also co-located with the galaxies in these filaments and knots. They may be the ionized gas may be the exact agent that strips dwarf galaxies of their fuel, the fuel needed for star formation. And that would explain this sort of correlation between the presence of star-forming galaxies in low-density regions and the absence of star-forming, low-mass star-forming galaxies in high-density regions.
I see. Is that somewhat of the goal of some of this research, is to fit this research into that, answering those kind of questions?
Very much so. Dwarf galaxies are of great interest for exactly, because they're relevant to questions of quenching, environmental effects on small galaxies. Very much so. We think dwarf galaxies, it's very clear that dwarf elliptical galaxies are the kind we're studying today. The fact that we really only see them in clusters, hardly ever see them in low density environments, is telling you something about the effect of the environment on how these galaxies form or how these galaxies evolve over time, how they change over time. So yeah, tonight's research is very much at the heart of questions like formation and evolution of dwarf galaxies. Not just DEs, but dwarf galaxies in general.
Excellent. Thank you very much. Very intriguing topic for sure.
Thank you.
I've got to wonder if there's time on James Webb scheduled for the study of dwarf galaxies. To any knowledge of that?
Absolutely. There are, there are particular studies of dwarf galaxies going on with Webb. In fact, some of the highest redshift galaxies that we see today, it's been very much in the news. 60 Minutes, CBS 60 Minutes carried an interview with one of my colleagues, Professor Brent Robertson was on 60 Minutes talking about James Webb images of distant galaxies. These distant galaxies that we see today, they are certainly not yet assembled into large structures like we have, like the one we live in. They're not, fully formed galaxies like the Milky Way. So they are actually low mass galaxies that are going to gather with them other low mass galaxies and merge together to form bigger galaxies. So that's an example of James Webb studying. Whenever James Webb is studying very distant galaxies, is also studying low mass galaxies, because there were very few galaxies of high mass at very high redshift, galaxies formed in small building blocks. This is also what makes our studies of DEs relevant, that we think that these may be examples of low mass galaxies that never got a chance to merge with other galaxies and become much bigger galaxy units, galactic units. These are sort of, we're seeing the building blocks themselves. They haven't assembled into larger units. Yeah, so definitely relevant for Webb. Webb has studies of nearby dwarfs as well, not just very distant low mass galaxies. I'm not directly involved in any of those. I'm involved in James Webb study of star formation and chemical evolution in Andromeda's disk. That's something that's part of cycle 1 of James Webb. Cycle 2 proposals have gone in. They're being reviewed now.
excellent. I so appreciate you folks making this available to us to witness this this leading scientific cutting edge research you folks are doing. Thank you very much.
Thank you, Tim. Rob, the
thanks, Tim.
class, what happens is it's not the charge necessarily that keeps the ionized gas from forming stars. Rather, what keeps it from forming stars is this gas has been heated to high temperatures. The molecules, the particles are moving very fast, and because they're moving very fast, they have high pressure, and that's counteracting gravity and holding it up against collapse. It's that high pressure that leads to high-speed collisions of the atoms that leads to them being ionized. That's those high-speed collisions knock the electrons out of the atom. So there's a correlation, but not causation. So it's not the fact that they're charged that causes them, that prevents them from collapsing, but rather it's the fact that they're at high temperature that both causes them to be ionized and causes them to resist gravitational collapse.
Okay, so the ionization is a
result.
A result of them being high temperature. Okay.
High temperature, exactly. If there are no other questions, I will, I'll hang up this Zoom call so that Arena and Joel can go back to the Keck Zoom link. And I'll try to catch some sleep because I have to get up at 6 a.m. my time and it's a little past 1:30. Thank you, folks. Please keep coming back and tell others about it. Here, love to have more people join.
Yeah, thanks for coming out, everyone. It was a pleasure speaking with you all tonight, and yeah, really appreciate the thoughtful and fun questions that you've been asking. It's nice to interact with people and people that are interested in this kind of science. So yeah, keep coming out.
Thanks a lot.
Take care.
Bye, everyone.
See you, Rob. See you, Ian. Rina, I'll see you a little later on the other Zoom link. Ian, I'll catch up with you later. Ian, take care. Rina, I think Joel has moved over to the Keck Zoom link.